So now let's write a few tests for our stablecoin. Let's go to the index file where we have our ERC20 tests, and let's just get rid of all of this for now. And if you still have it in the ERC20, we still have this mint call here in the constructor, which of course we don't need anymore, since now we have minting and burning in our stablecoin directly. And now we'll only go over a few example tests, because obviously testing more complex contract like the stablecoin requires a lot of testing, especially all the edge cases to be tested. And since it's a lot of code to write, I've just prepared this here for the first two tests that we'll take a look at. So it's the beginning essentially the same as we did for our ERC20 contract. We first deploy the stablecoin inside the first before each. And to deploy the stablecoin, we of course need an oracle. And so we have to first deploy an oracle contract here. And then we just set a price and say, okay, the ETH/USD price is now 4,000. And we just say fee rate percentage here is 3%. And then in our first test, we just, for example, you could just test if everything is deployed correctly by checking, okay, fee rate percentage is in fact this 3% that we passed along. And then the actual real test is if it allows for minting. So here we actually just call the mint function on the stablecoin, and we will pass an ETH amount here. And since ETH, we actually have to convert it to the Y unit. And for that, you can use from the ethers library that we've already used in the ERC20 tests. And you can just use that here. And then .utils.parseEther is a nice functionality to just convert this amount into a Y amount. And it will be passed as big number type. And then you can just pass this as the value, so the amount of Y passed along in this mint call, since it's a payable function. And then afterwards, you check the function here, total supply, and it should actually be the amount that is the amount of ether that we pass along times the price. And this is the first simple test for minting. So now let's add a test for the burning. And of course for burning, we require that there actually has to be something minted first. So I have just copy pasted this here again, so it's quicker since it's a lot of code. So in the case for burning, we add a describe that says with minted tokens, because only when there are minted tokens, we can actually burn something. And so in the before each, we first now mint this amount, mint amount, and then we can write a test that checks for the burning. And we burn an amount that is basically the mint amount that we originally minted, minus whatever we say here as the remaining stablecoin amount. So of course, this remaining stablecoin amount should in fact be smaller than the mint amount. So if we say mint amount here is ETH amount times ETH/USD price, it would be 4,000, right? Because we defined this here as 4,000. So then we would expect here to pass 4,000 minus 100. So we burn 3,900 of the tokens, and we should afterwards still have 100 stablecoin tokens left. Now we have some basic tests for burning and minting the stablecoin. Now we can actually go towards testing depositing and withdrawing this collateral amount, and they will of course then create the depositor coin. And so as a first test, I have again this one here, which is testing that we in fact require someone to deposit this initial ratio of collateral. So if you remember, we just hard-coded this as 10%. So since we have currently deposited 1 ETH for the stablecoin in our system, 10% of that would be O.1. So now the first person who's calling deposit collateral buffer has to deposit at least O.1 ETH. And in this test here, you can see we actually deposit O.05 ETH, which is actually less than the minimum. So in this case, we would expect it to revert. And this is similar to this revert test that we had in ERC20. You call await, expect, and then the function call. And then on this whole thing, you do to be reverted with. The only difference now is we have a custom error. So then the string that we expect for it to be reverted starts with this custom error. And in here is the amount, this expected minimum amount. Of course, we have to convert it again as a actual Y value. And yeah, we can test that this is actually the case. So now let's have a look quickly that all the tests we wrote actually are working so far. And yes, they are. So that's great. So now we can also add a test for a deposit collateral buffer which doesn't revert. So we have to add a minimum deposit O.1 ETH. And I again have to test here. And what we'll do here is we'll deposit O.5 ETH. So now this deposit collateral buffer call will not revert anymore. And then, of course, what happens is in our stablecoin, we deploy a new depositor coin. This was here in this case here, where we now deploy a new depositor coin in the contract. So now, how can we actually use this in our test? Well, first of all, you can create this depositor coin factory like we used to, but now you don't deploy a new depositor coin, obviously, because it's already deployed. So we have to somehow attach it, and that's the attach function that you can use on the factory. And then you pass just the address to this attach function. And the address, well, that is available from this depositor coin view function, because the depositor coin itself in our contract is, of course, here public state variable. So we can just read it directly and pass it to the attach function here. So now we have a depositor coin that we can actually call functions on. And well, what is the expected total supply of the depositor coin? Well, it's the new initial surplus in US dollar. So it's the stablecoin collateral buffer that we send along, so O.5 ETH, times the ETH price, and that should be the total supply. So if we're looking at our example here with an ETH price that we defined as 4,000, now we're passing 0.5 ETH and times the price of 4,000. So we have actually a surplus now of 2,000 USD in the contract. So that should be the total supply as well. And now lastly, we can test the withdrawal of the collateral buffer. And for that, of course, the contract needs to have deposited collateral buffer again. And so we need another describe. And I have this here. And also pay attention to where I just copy pasted this. So I'm pasting it in this describe, which already contains the before each for the minting. So in here now we create a new describe that says with deposited collateral buffer. And so then, not surprisingly here, we first deposit collateral buffer. Well, basically what we did before in the test, but now we do it in the before each. And again, we set our depositor coin as this new value that was deployed. And then we can actually write a test to test the withdraw collateral buffer here. And then the amount of depositor coins that we will be burning here, we will define here as, first of all, we look what the current depositor total supply is. Well, that's basically what we did before, which is the buffer times the ETH USD price. And then we just say we burn 20% of the total supply and use that as the burn amount here. So then we call the withdraw collateral buffer, and afterwards we check the total supply now, of course, of the depositor coin should be what it was before minus the amount that we just burned. So let's have a look if this is still all working. And yes, all tests are succeeding. And of course, we are only testing a fraction here of what the actual logic is. So don't think this is like proper testing here. There are many edge cases that we haven't tested. And even in the test cases itself, of course, there is more logic that we could test on not only the total supply here. But I will be adding all this code along so you can take a look at it. And the homework as well will be writing one additional test case, which will be depositing more collateral buffer now in the case when already someone deposited, because that's actually something that we haven't tested at all yet. And it's a little bit trickier, but I think you can do it.